Welcome everyone today. We have Minoru Osawa, who's a colleague of mine at Kyoto University, the Institute of Economic Research. And as ever, clarificatory questions during the presentation are welcome, and we've got time for a bit more uh, chat and deeper discussion afterwards. So over to you, Minoru.
Yeah, thank you. Good afternoon, good evening, and maybe good morning. Thank you for having me in this wonderful seminar series, and also thank you all for joining my talk. As Jonathan introduced, I'm Minoru from Kyoto University, and actually working on urban and spatial economics, not very much evolution, but anyways, this talk is about sort of evolution or population games. And today I will talk about equilibrium distortion with zero noise, based on what I call the sampling logit approach. So this talk is about a simple framework on how choice behavior and so equilibria change when two kinds of boundedly rational behavior interact. It's still at a very early stage, so any suggestions and thoughts are very, very welcome. So please go ahead. Let me start with broad motivation. Models of boundedly rational behavior are widely used in both theory and actually quantitative economics. So, for example, random utility models, RUMs, are core tools in transport demand analysis as well as quantitative spatial economics, which actually I'm originally from. But in bounded rational choice, there are, I think, essentially two sources of noise. One is idiosyncratic errors, which standard RUMs can capture or maybe do. And the other is limited observation, which arises from imperfect information on the side of agents. Maybe they cannot observe the true state of the world. My question is that how these two kind of these noises affect equilibria in large games. That's it. So maybe more backgrounds about two kind of noises. So the first one, idiosyncratic noise, as in RUMs, are essentially a quantitative tool to address irrationality in choice data. So actually, McFadden in 1980s developed RUMs for transport demand analysis in the first place. And then transport scientists or engineers introduced logit equilibrium in trans-network equilibrium problems. Like Joseph Sheffi, it's like 40 years ago. And then in these days, quantitative spatial models use RVM theory to model like structural modeling. And in the context of games, quantum response equilibrium is introduced to sort of explain experimental data. Here also, in my understanding, their motivation was like smoothing out irrational behavior. In this context, idiosyncratic noises are convenient tools to fit data. On the other hand, there is another source of noise, as I said, which is based on finite observation of the reality. In this context, this is more of models of micro behavior. For example, the most related works are choice and equilibrium and imperfect state observation, introduced by Osborn and Rubinstein in like 2003, or maybe a bit earlier than this. And recently, corresponding dynamics has been extensively over by explored by some people. And also, another related context is equilibrium selection under these kind of settings. So these are my broad background and related works. With this background, my objective is as follows. This study introduces a new choice rule which I name sampling logit choice, which just combines logit type noise and sampling limited observation. And because I introduced choice rule, the corresponding stationary concept, which I name sampling logit equilibrium, is also defined. And I also introduced the corresponding evolutionary dynamic, but on this point I haven't explored much, so my talk is based on these two parts. And the results are as follows. I show that this choice rule naturally connects to previous literature in equilibrium selection. And this is a bit of a simulation-based exploration. And another is that I show that this equilibrium can be interpreted as the emergence of virtual preference for variance that endogenously emerges from these two kinds of noises. So I also gave some comparative statistics on how this equilibrium depends on noise parameters. So that's my introduction, and maybe let me share my slides in chat. I think I did so. Let me dive into my environment. So I consider large population games with single population. So there are homogeneous and anonymous continuum of agent, each of whom choose a pure action from a base action set, which is fixed throughout. And then the population state is a distribution X, where Xi is the mass of agent playing action I. So yeah, I know everybody is familiar with this context, but let me be clear. So given this distribution, the payoff function is a mapping that assigns the payoff for each action. So when this S is given, the payoff function F fully identifies the population gain. And actually, this framework, I think you all know, fits very well in the context of spatial and transport works. So, because there are many people and there are like discrete possible actions, for example, where to live in which region to live or which route to take. So it's a very my sort of models. So examples of population games includes random matching in symmetric normal form games, where Aij is a payoff of playing action I and matched to other guy playing action J. So in this case, expected payoff is Fi is Aij sum, like weighted average of these Aijs, or Fx is Ax just. So in this case, this payoff matrix identifies the game. And the other important class of population games would be congestion games. And it's a network equilibrium model in transport engineering, and proposed by Beckman and others in 70 years ago. For example, if S is the set of alternative routes over a network from your residential area to central business district, then the payoff of taking route I in the morning would be minus the travel cost of I when the route choice pattern is X. So this is congestion game, and it's a very important class of population games as yeah. So this is an environment. And then, given this kind of games, we can introduce various stationary concepts. So the most important or basic one is, of course, Nash equilibrium, which is a fixed point of best response correspondence. So best response correspondence BR is a mixed strategy best response on which only payoff maximizing actions have positive weights. And we can introduce limited observation to this. So we can introduce in many ways, but in this paper, I focus on action sampling of others. So if an agent receives a revision opportunity, the agent first observes K others. So K people. So looks at how which action they play. So this sampling determines the count distribution, where Zi is a number of agents playing action I in that sample. And then the agent decision maker forms the estimate of the population state. So in this study, I assume the ML estimate, meaning that the estimate is just the empirical distribution. So then they best responds to the inferred payoff based on this empirical distribution, which is f of w. Then they best respond to this inferred payoff. So just if the draw is it, their best response is this. So the resulting choice rule is this time the probability of that and summed over all possible samples. So basically the expectation of this BRW. So induces this K parameter, the best response, no, K sampling best response correspondence and the sampling equilibrium or K sampling equilibrium is a fixed point of this map. Okay. So these are like the existing concepts regarding Nash equilibrium and combined with sampling. Then another major equilibrium or stationary concept is logit equilibrium, where when the payoff vector is fi of x, then the probability of choosing action I is this. And eta is the noise parameter, where the closer to zero, when eta is closer to zero, this approximates the best response. And the logit equilibrium is a fixed point of this. So in this study, I just simply combine these two models. That is, in K eta sampling logit choice, in this choice rule, each agent again draws sample and forms the estimate of payoffs, and then just logit responds to this. So the choice rule is the expectation of logit choice probability based on this estimate. So we just replace the best response map here to logit choice map. That's it. So this is a bit straightforward, but this is a natural straightforward, so a natural generalization of the previous literature, I suppose.
That's right. So can I just to
Sure.
clarify, so we have the sampling um, um, dynamic, which samples and treats the sample empirical distribution as if it were the true distribution
Yeah,
and
yeah, yeah.
lets best respond to that. And then we have logit, where people do the typical logit responses, and this is just putting them together. So you
Yeah, yeah,
sample and you logit respond to that. Okay, very simple. Thank you.
yeah. Yeah, yes, so this is very simple, but yeah. Yeah, I suppose not, it's not sure.
No,
So
absolutely. I'm just like clarifying for
yeah, yeah,
everyone.
sure,
I
sure.
ask boring questions. It's a
Yeah,
trend.
no, no, no. So given four choice rules, we can just introduce myopic corresponding myopic dynamics. I think it's straightforward. So these are the dynamics in the literature, and if we replace this part by our choice rule, you get the dynamic. So yeah. So these are the model is just this. So I introduce some. No, no. Our model is oh my, just this. So I explore some specific games. So let me consider the simple 2 by 2 coordination game where strategy one is payoff dominant and also risk dominant. So no, no, no. It's a wrong statement. Let me line by line. So yeah, I consider this game where action Nash equilibriums are 0 and 1 by 3 and 1. So the best response map looks like this. So the equilibrium are just these, of course. So under the best response dynamic, this equilibrium is locally unstable, and these are both strict equilibrium and thus locally stable. So it's a known, very, very well known. And this equilibrium is selected in under various rules. This is a known result. So what happens if we apply the sampling logit choice rule to this setting? So this figure compares the sampling logit choice rule and sampling no, without the typical logit without sampling. So this thin black line is a basic logit choice map. So there are oh my, 1, 2, 3 equilibrium. And these broken lines and this one line is sampling logit choice rule with fixed eta, the same eta as this logit choice map. So as expected, if you increase the number of observations, draws k, it's just become closer to logit choice map. I'm just now confirming the expected behavior of the choice rule. So next I compare the sampling logit, which I proposed, and the sampling best response at k being 5. So as expected, if you diminish eta, it approximates this sampling logit, sampling best response rule. So as in the logit figure, this thin black line is the sampling best response. So it's already noisy and it exhibits a smooth curve. But when the logit parameter is large, the sampling logit is much more noisy and there's only one equilibrium. But anyways, if you decrease eta, this our choice rule now converges to the sampling best response rule. So this is a large eta, and when eta goes smaller, you go this way. And yeah, it's natural. And what these points, these crossing points, which are equilibria look like? So now we take eta as the horizontal axis, and the vertical axis is x1, and the curves represent equilibrium curves. When eta is 0, it corresponds to Nash equilibrium, these points. And so this thin black lines represent logit equilibrium. And we, as in the literature knows, that if you diminish eta, make eta smaller and smaller, these curves converge to this Nash equilibrium. And our sampling logit equilibria also exhibits a natural properties. So if you take k to infinity, which I haven't, but actually if you take k to 20, it is these pink broken lines. And for upper branch, you are already sufficient, very close to logit curve. And if you actually take this k limit, you just converge to here naturally. And if you make it smaller and smaller for each curve, you converge to some sampling equilibrium. So for this pink broken curve, this point is 20 sampling equilibrium. And if you just take these both parameter to these limits, you just converge to here. But for sufficiently large k, it's just converge to approximate equilibrium. So if you focus on this part, our approach yields equilibrium selection as eta goes down from relatively high level, like here, and it's sort of consistent with the literature, like Kleindler and Young, and I see the other is Cherokee work, I believe. So I'm just confirming the like expected behavior. So another specific example. In this figure, I focus on I'm looking at Young's game, where the best response dynamic does not select one specific equilibrium. So this is a three strategy game where all corners are strict equilibrium. And if it is known that if you introduce sampling noise, if you consider sampling best response dynamic, this dynamic selects this corner. It is done by Oyama Sandro Telshu. And the logit version is this. So this is logit choice, logit dynamic, and this dynamics does not select one, but there are two. But if I again introduce sampling noise, we can select one stationary point. This is not a Nash equilibrium, but sufficiently close to this corner. So, and maybe the trajectories are more straightforwardly going this, so it could be faster in some sense, but I'm not sure because I haven't done any formal analysis on this respect.
Have you got the payoffs for this game?
Oh,
People might be
oh,
interested to see the payoff
sure.
matrix if
Uh,
it's easy.
it, yeah, let me let me share different screen.
If it's troublesome, just leave it till later on, and that's fine. So uh,
I think I can maybe later.
just leave it till later. Yeah.
Yeah, yeah. Hmm. So it's just the exploration of our choice rule and dynamic. So summary so far is like this. Sampling logit choice is a natural or straightforward or simple extension of existing literature, but it's sort of natural, I'm not sure how to say it in English. Yeah, it's natural counterparts of sampling equilibrium or logit equilibrium. If you introduce sampling noise, you get sampling equilibrium, and then you add the logit noise, then you get our equilibrium concept, and either way you can come here. So about only equilibrium selection, as we explored, there are natural analogies to known results on equilibrium selection, like selection result in logit KRE and selection in sampling best response dynamics. And more directly related work is Kleindler and Young, which considers some limited observation and logit choice, but a bit the focus is a bit different. But yeah, I needed to like more. So on this aspect, I'm still not to work. My work is still in progress. So I think I can build some connection between their results. So and that's exploration of natural properties. But a bit not satisfied because I'm not sure how and why the two kinds of noise distort equilibrium. So I want to understand the choice rule a bit more like intuitively. So it's a not intuitive. So if you have some simple representation of this part by maybe x or important parameters such as eta and k, maybe I have like more insights or into the behavior induced by this choice rule. So I just tried to this on this respect. So basically, I approximated this expectation by simple delta method. So to obtain a simple function or that approximate this. So in fact, I can show that this is a function of x and variance of sample count and info of f at x, and of course k and eta. So it's a relatively simple function of x, these important parameters, so it could be easier to understand. So that's my strategy. So for simplicity in this talk, I focus on the linear payoff case. So in this case, tilde as an approximated function is relatively simple, and the nonlinear case is in the paper, and I introduce some notations. For any collection of I-dependent variables, I set logit weighted average by y bar, and the relative value with respect to this y bar by yi hat. It's a typical average mean payoff and relative value notation, but the only difference is here you have logit weights. Right? And with this notation, you get the approximation formula like this. So the approximation, oh no, I need I here. The approximated formula looks like this. This is a simple logit choice probability of action I. And this is a new term. So it can be seen as a eta logit choice rule p eta with a just multiplicative correction term. So this is just parameter. And if you, this part is actually the variance of relative marginal payoffs at x. For this is a relative marginal payoffs because for fx linear, you get this. This is ith column of this A matrix. And with this A, you get the relative value like this. And then you just compute this. This is, in fact, variance. And we observe that if you take k to infinity, this just vanishes. And so we recover the logit choice rule, which is natural. But you can't take eta just to 0 in this formula. Because if you take this eta to 0, this part includes eta logit choice probability, but it's bounded, so it doesn't matter. So, but on this in this part, if you take eta to 0, it explores. That's problematic. So So that invalidates the approximation because in if you take eta to zero, the logit choice probability is less and less differentiable. Yeah, it's differentiable, but more like behave like best response function, and it's less smooth. Yeah, less smooth. So this is just this type of scaling is required for the accuracy of this approximation. So in a sense, if you want to make this eta smaller, you need to make sure that k is more large and larger. So the caveat of this approximation is that that k is large. Anyways, so in this sense, there's a variance term. So actions with higher relative marginal payoff variances are chosen more often than the plain eta logit choice rule. Also here also. So on average, agents, it looks like they exhibit bias toward sort of risky options. But this is not an individual level behavior, but a population level effect. So it's a sort of aggregate preference for variance as a virtual preference for variance. And it arises endogenously from the two kind of noises. So actually, the induced bias can be written as a virtual payoff primitive. So like Joseph Hofbauer syndrome in 2007, there's a virtual payoff representation of logit choice by equivalent log penalty representation. So logit equilibria can be represented by log congestion term and Nash equivalence. Like that, we can introduce this penalty term to the base payoff function and obtain a partial payoff f tilde, and we can apply the logit choice rule to this virtual payoff to obtain our choice rule. Well, actually, the approximation of our choice rule is at xi again. So why does this variance premium emerge? So it's basically Jensen inequality about the exponential, but let me explain a bit. So let me consider this exponential map where mu is a kind of payoff. So we have this payoff evaluation error based on finite sampling. And suppose it's for simplicity that this error can take this to from plus minus zeta with equal probability. But because of the convexity of exponential, positive errors increase p more than negative errors decreases it. So this difference is bigger than this. So it's Jensen's inequality, but expected value of this exponential is upward biased. So this kind of bias shifts like upward error more like pronounced. So and also this size of this upward bias can be is proportional to the variance of this error, this payoff evaluation error. Further, in our context, this epsilon is actually represented like this. This is inferred payoff minus true payoff, which is in this to the first order, we can represent this, which is obviously related to sigma, which looks like this. A bit different, but a bit different because the relative value of this variance matters. So because logit choice probability is based on the relative values of this, and this discussion matters in relative terms. So a concrete example. So if we consider again the first coordination game as the example, the first example, specific example we considered earlier. The approximation looks like this. And let me focus on the choice probability of action 1, which is in approximate terms looks like this. So let me plot this. So for this coordination game, if x1 is in this range, the best response is action 2. So usually in eta logit choice probability, action 2 has larger weights and action 1 has smaller weights, smaller weight. But our approximation shows that for this range, the probability of choosing action 1 is upward biased. So our two types of noise combined, in our setting, payoff estimation errors introduce bias towards suboptimal choices. And yeah. So because our noisy setting introduces bias towards the suboptimal choice, comparative statics of the interior Nash equilibrium have intuitive signs. So for example, if you increase eta for large K, the interior equilibrium, which is this, it shifts. If, I'm sorry. So more to this direction, meaning that the region of attraction for action risk dominant equilibria or its approximated version will enlarges. So a similar claim applies for K. So I think this is very much related to fast convergence and medium eta and the partial observation, but it's still work in progress. So actually, that's it, what I have now. So let me summarize. So I propose and analyze the simple yet new choice rule, the sampling logit choice, that combines two standard noise structures. So because of differentiability of logit, I have a clear approximation formula, and it have intuitive interpretation as virtual payoff or in a sense, variance premium in a sense. And it's, as I said, it's still at an early stage and many to do. Among these, the most important one would be analyzing a bit large class of game, but large but important class of games such as stable games or potential games, and also concrete application to, for example, bilingual games with more than three actions would be interesting, I suppose. So, thank you for your attention.
Thank you very much. Thank you very much. Okay, I'll stop the recording and we can pass to questions.